What is light? Is it a particle or is it a wave? What an imprudent question. As we know, these are not mutually exclusive characteristics. Particle describes the composition of a substance, and wave describes the motion of it, right? But wait, so that still doesn't answer the question. Is light a particle or a wave? Let's find out. Today we're going to add a new piece of equipment to our laboratories and perform a mind-boggling experiment with astronomical implications. First, we will be constructing an interferometer, a useful piece of experimental optical equipment capable of performing a variety of tasks in a laboratory setting, including the Michelson-Morley experiment, the Sagnac experiment, and others. Specifically, though, we will be building a common path interferometer. Our version will be taking the approach of physicist Robert Young's 1801 double-slit experiment. So our interferometer will split one single beam of light into two by passing it through two small openings. Next, we will examine characteristics of moving particles and those of waves moving through a substance. We will then use our new interferometer to perform the double-slit experiment ourselves. Next, we will observe the result and compare it to what we learned in our previous experiments. You'll be astounded at what you find. Let's begin. Before we get started on this project, there's a few things we'll need. Unlike the experiments of the 19th and 20th centuries, our projects can be made from now easy-to-find materials and built in a way where the experiment can be accurately replicated anywhere and performed a multitude of times with ease. Robert Young found that the sun would be the optimal light source for his experiment, and it was, at the time. The problem is that most light sources emit their light radially, out in all directions, which then crisscross. The sun does too, but since it is a great distance away, the sun's rays are nearly parallel. Think, a radius of 1 centimeter makes a sharp curve, but a radius of 1 kilometer looks almost like a straight line. So, the sun is a fairly good light source, but a laser is better. A laser beam is a highly parallel light source, which is what allows it to travel a large distance and still appear as a small dot. The parts you'll need for this project are a laser, 630 nanometers is what I use, and it's 4.5 volts. One project box, 2 insulated wires, 3 AA battery holder with switch, 3 AA batteries, make your own by checking out my other Instructable, 1 32 AWG copper wire, 1 or 2 wire connectors, 1 PVC pipe with a cap, 1 plastic ramekin or similar item, some shrink wrap tubing, and tools. You'll need a drill, a large drill bit, a small drill bit, a sanding bit, a hole punch, a soldering iron and some solder, scissors, glue, and various tape. Masking and aluminum tape or electrical tape will work. Make do with what you have on hand if need be. I painted a metal cookie box black for the enclosure. A small plastic dish will work in place of a ramekin. Inexpensive lasers are typically more than sufficient. Please feel free to get creative with the rest of the parts as well. Always read warnings and take cautions when working with lasers. Next, we're going to prepare our battery pack. Heat your soldering iron and strip the ends of the battery holder leads and insulated wire. Slip on some shrink wrap and extend the leads by soldering on a length of wire to each. Before you're finished, insert your batteries and lightly tin the ends of the wires to prepare for the next connection. If you don't have any AA batteries, make your own. See how by checking out my last Instructable. Wire up your laser. To wire your laser, we will need to make a quick modification. In order to take data while experimenting, we'll need to leave the laser on for extended periods of time. This means we'll need to replace the button with a switch and replace the batteries with some of a higher capacity. The battery holder we just prepared will serve both these purposes. We'll just need to connect it. To access the leads, we'll first remove the laser's battery cap and remove the batteries. Next, grind down one side of the laser's case, as shown, or cut it away however you see fit. According to the original battery orientation and the diagram, the spring is the negative ground and the case will serve as the positive lead for the laser. With your soldering iron, attach one wire to the spring and use a piece of shrink wrap to secure and cover the spring to avoid shorts. Then, drill a small hole in the case. Wrap your positive wire around securely. Solder in place and shrink wrap that connection as well. Connect the ends of your wire to your wire connector. Your laser module is now complete and ready to be temporarily wired up to test your connections. Once tested, continue on to the next step. Assemble a double slit. We will be replicating Robert Young's double slit experiment and will need an appropriate setup. To do so, we'll attach our tape to create a rectangular slit with a wire placed precisely in the center to create two parallel, uniform, evenly spaced slits. First, wrap the laser module with tape to firmly hold down the laser's on button, and so that fits snugly in the piece of PVC pipe. Then, hold a straight piece of wire directly over the laser's lens, as shown, and tack in place with glue. Make sure the wire is centered, straight, and taut. See the photos. Next, cut two pieces of tape to go on either side of the wire. Electrical tape will work, but aluminum tape results in a crisp, straight edge and yields the best results. Lay each piece parallel to and on either side of the wire, just like the photo. You will want to leave a gap equal to the width of the wire for uniformity. Carefully connect the power, turn on the switch, and aim the laser at a smooth surface to test. Some adjustment may be necessary. You will be able to see a vague result, which will be improved upon once your interferometer is assembled and steadily pointing at a distant viewing screen. If everything works, put your laser module to the side. Assemble laser mount. We will need our laser to sit straight and horizontally level for the best results. We will insert the laser in the PVC and mount the PVC in the end of the project enclosure. First, measure placement for a hole to allow the wires from the laser to pass through. To do this, drill a hole and smooth the edges with your sanding bit. Use the sanding bit at an angle to avoid kinked wires. Next, drill a centered hole in the side or end of your project enclosure. I used a tall box on its side to allow removal of the lid and mounted the laser there for easy access. The hole should be large enough for the pipe to fit through, but not the cap, which, with a little glue, will hold it in place. Apply glue, hold straight, apply pressure, and allow the glue to dry. Lastly, drill another large hole with your hole punch bit centered on the end across from your laser for the light to exit the box. Then, drill a hole in your ramekin or cap and glue it around the hole you just drilled to cover the rough edge and signify where the light will exit. Assemble all components. Now it's time to put everything together. Glue the battery holder somewhere on your project enclosure that is convenient and close enough to the laser for the wires to connect. Depending on your enclosure, you may need to drill a small hole for the wires at this point as well. Your laser mount should now be dry and solid, so insert the lead wires for your laser into the PVC and pull them through the hole you drilled, and press the laser in behind it until it is snug and straight. Next, feed the battery leads into the enclosure. Connect to laser and close box or attach the lid depending on your particular enclosure. Finally, cut out and attach the warning label from your laser for safety. Your interferometer is now complete. Flip it on and make sure everything works before we begin our experiments. Now, let's hypothesize. What happens if particles pass through two slits? To put your new interferometer to use, we will be performing one of the most important experiments in all of science. Upon performing this experiment, we will be able to answer one of the most prevailing questions in physics. What is light? Is it a particle or a wave? To answer this question, let's hypothesize what light will do when it passes through two slits. To do so, let's consider the following. If particles are propelled through two slits, what will happen? How will they react on the other side? Let's find out. To find out what happens when particles pass through two slits, we will consider this. If we take a piece of board and cut two slits in it and place it in front of a clean surface, what will happen if we spray particles of, say, spray paint at those two slits? Try for yourself, or see the images for the result. When particles pass through the slits, the particles are split into two groups, which appear as two marks on the surface behind the slits, as shown here. Now let's think about what happens if a wave passes through two slits. If one wave passes through two slits, two identical waves will emerge on the other side from their respective slits. Let's see if we can identify any characteristics from this event. First, let's observe one wave on its own in the first image. Next, by simultaneously making two waves of equal wavelength and magnitude, we can observe how they interact. Since they are identical and in phase, this is analogous to the output of our double-slit experiment. What we find is that along any line perpendicular to the direction of travel, we see a series of waves, troughs, and flat areas. The flat areas occur when one's crest intersects with the other's trough, canceling each other out. The only way this can occur is if it is two oscillating waves, areas of high and low pressure, moving through a substance, and not actual directional motion of the substance itself. Now let's hypothesize what happens if particles moving in a wave passes through two slits. The question has been posed, is light a particle or a wave? But light has been proposed to be particles moving in a waveform, referred to as the wave-particle duality of light. So, let's see what happens when particles moving in a wave pass through our double slit from earlier. With our double slit and a screen placed behind, we will again spray a stream of particles through the slits, but this time the particles will be moving in waves on the X, Y, and Z axes in three separate experiments, respectively. We will also remember the results of our linear particles moving through a double slit as our control experiment. Then we'll move the source on the X-axis, then on the Y, and finally on the Z-axis. When we're done, we'll compare the results. Let's begin. My results can be seen here. What we find is that when the particle source is still, it results in a pattern on the other side of the slits that very much resembles the shape of the slits. When the source of particles is moving on the x-axis, left to right, a wave on the x-axis is created over time, which results in a slightly wider pattern on the screen behind. When the source of particles is moving on the y-axis, up and down, a wave on the y-axis is created over time, which results in a slightly taller pattern on the screen behind. When the source of particles is moving on the z-axis, back and forth, no difference can be seen as compared to our control. Note that in none of these instances does an interference pattern appear. That would be impossible. Now with our double-slit interferometer, we can pass a single light through two slits, and out will emerge two bands of light. What do you think the light will most closely represent in this instance? Will the light emerge as two groups, as the particles of spray paint did? Or will the light emerge as an interference pattern, a series of wave cancellation, wave cancellation, wave cancellation, etc.? Let's dim the lights, flip on our new double-slit interferometer, and find out. Turn on the laser and point the light at a smooth, non-reflective surface. What do you see? What we see is nothing like passing particles through two slits. We see a clear interference pattern. If light were particles, they would build up in two distinct areas, not cancel out. What we are seeing are the multiple ripples of the light wave, with clear interference patterns where these ripples intersect. The only way that this can occur is if light is not particles. Light is a wave. Well, congratulations. With this experiment, you just unequivocally and without a shadow of a doubt proved that light is a wave. It makes sense though, right? Light is measured in wavelength. Changing the wavelength changes the properties of light, its color, etc. When an electric light bulb emits light, it is not emitting particles. It is emitting a variation of the wave of electricity from which it is supplied. What are the implications of what we just learned? What you will realize is the paradigm-shifting reality of the nature of our universe and our place in it. What about all the talk about wave-particle duality of light? Well, like we discussed earlier, as we know, these are not mutually exclusive characteristics. Particle describes the composition of a substance, and wave describes the motion of it. We obviously don't ask, is the ocean made of water or waves? It's a foolish question because we can see what the ocean is. It is water moving in the form of waves. Now, after this experiment, we can similarly see what light is. So, what about the evidence that light is a particle? Well, pressure of light experiments show that emitting a light on a lightweight, balanced object can propel it, but this could be explained by the heat differential created by thermal expansion on the side of the object which the light wave is projected. No photons would be necessary. If light is a wave, then it needs something to pass through, right? The Michelson-Morley experiments aimed to prove just that. They were unable to detect the motion of such a substance, which they referred to as ether. They did not, however, disprove its existence. What do you think that means? These and many more have been explained by the particle nature of light theory, which has just been proven to be incorrect. So, what substance do light waves vibrate through in space? How does the sun's light reach us? What about Einstein? The invention of the idea of the photon was developed progressively by Albert Einstein over the course of his career to purportedly elucidate experimental observations that he could not explicate by the classical wave theory of light. By overtly dismissing the long-standing equations of James Clerk Maxwell, albeit apparently minutely, novel profusions of models were able to emerge. These models, though, were dependent on the inconsistent assumptions stated in Albert's 1905 on the electrodynamics of moving bodies, his theory of special relativity, which postulates that light is always propagated in empty space with a definite velocity c. Einstein defined light as composed of photons, matter that moves at the speed of light. Particles of any mass, no matter how minute, would have the momentum to displace anything in its path, including our planet's atmosphere. So how did old Albert explain this? He said photons were massless with momentum. Well, any student of physics knows this is impossible because P equals m times v. Momentum equals mass times velocity. If mass is zero, momentum is zero. Looks like Einstein needed a refresher on basic physics. On this fact, among many others, relativity falls apart completely. Einstein had it wrong. He never bothered to perform experiments which precluded him from seeing the truth. No amount of experimentation can ever prove me right. A single experiment can prove me wrong. That's a quote from Albert Einstein himself. With these findings, the implications are endless. If light is a wave, as we now know it is, it must need a substance to pass through. What is this substance of which we are at the center? Can we apply this newfound knowledge to electricity as well? Does that mean electricity does not require free electrons and can be transmitted wirelessly? If light is not a particle, does that explain the photoelectric effect? Is the vibration of light simply being converted to a different frequency? What questions do you have? I know I had plenty. Leave your questions in the comments and let the inevitable debate begin. I'll depart with a couple quotes. I will never have greater respect than for the man that realizes he was wrong and graciously admits it without a single excuse. Anonymous. It is easier to fool people than to convince them that they have been fooled. A great quote by Mark Twain.